And we have arrived at the part of the course concerned with Fuchsian groups, which are certain class of subgroups of PSL2R, or more accurately, of the group of orientation preserving isometries of the hyperbolic plane. One of the main features of Fuchsian groups is that they give rise to Riemann surfaces in very concrete ways. That is, they allow to construct Riemann surfaces in very concrete visual ways. Now, Fuchsian groups are going to be defined to be certain subgroups, to be the subgroups of PSL2R that satisfy certain property, and I would like to arrive at that properly naturally, and that is why I'm going to start with a motivation, which provides Riemann surface structure for the torus, and then we are going to arrive at certain property, and later on we are going to ask ourselves about the subgroups of PSL2R that have such property. And the answer is going to be that those subgroups are the Fuchsian groups. So first, a definition from basic algebraic topology, and it's what is a covering map or a covering function. Yeah, so first, suppose that I have two topological spaces and a continuous function p from y to x. We say that an open subset of the target of the codomain is evenly covered by the function if the following happens. If, and look at this picture, if when I look at the pre-image of B under P, such pre-image is the disjoint union of open sets of Y, the domain of the function, all of them open and pairwise disjoint, and with the additional property that each of them is mapped homeomorphically onto V by P. So in this picture, V is evenly covered. That V is evenly covered is sketched as drawing open subsets of Y, each of which must look like V because it's mapped onto V homeomorphically by P. And this is the usual so-called stacked pancakes picture above V. So in that case, we say that V is evenly covered. And we say that the map itself is a covering map if around each point in X, around each point in X, there is an open neighborhood which is evenly covered by P. So in other words, X has some open cover consisting of open sets, each of which is evenly covered by P. That is a covering map or a covering function. And we say that Y is a covering space of X. Now, some formalities. We're going to be, working with topological groups and topological spaces, and certain actions of certain groups on those topological spaces. and certain subgroups of my topological groups. And in both situations, we're going to be taking the quotient, and more accurately, the set of left cosets of the subgroup of the topological group. And we are also going to be considering the set of orbits of the actions on topological spaces. Okay, in both situations, we are going to be endowing the corresponding quotient sets with the identification topology, which is here you can see the definition. So the identification topology, you see, if I'm given a topological space, a set, and a surjective function, just as a function of sets, the identification topology for X, right, with respect to that makes P an identification. Well, one imposes a topology on X, and one wants to impose a topology under which P is continuous, of course. But of course there is an obvious answer, which is, okay, just take X and the empty set to be the only open sets, and of course that makes P continuous, but that's useless. Right? So one really wants to put as many open sets in X as possible without losing the continuity of P, and then one arrives at the conclusion that what one needs to define as open sets of X is precisely those subsets whose pre-image is open in Y. Yeah, so this is this and this is just a reminder, and the kind of all the formality surrounding the identification topology. Yeah, and then as I said, whenever I form a quotient or a set of cosets of a topological group, I'm going to be imposing the identification topology. And also, when I take a topological space and some group acting on X, I'm going to impose the identification topology in the orbit set. Now, this was kind of just some sort of interlude, right? Because I was speaking about covering maps. So one of the first examples one always sees is the covering of the circle by the real line, and it's done by this exponential. And then this kind of stack of pancakes, this sort of a tower of pancakes stacked above V. If you want to see how it looks like, it's sketched here, right? So somehow here around the complex number 1, somehow this would be my V, and then the pre-image would be all of this. So this would be like the corresponding pancakes, if you want, for this choice of V. Another example is the projection from the real numbers to the quotient. Right? So when I consider just the subgroup Z of R, yeah? So the projection to the quotient group. That's also a covering map. It's easy to check, so I leave it to you as an exercise. And then the next exercise asks you to prove that this covering map and this covering map are essentially the same. and formally is that there is a homeomorphism between the covered maps that makes this covering to correspond really to this other covering, so that somehow the homeomorphism is really just kind of a relabeling of name of the points of the spaces. So that I leave as an exercise. And now I'm going to move one dimension up. Right? So I'm going to, so from this one-dimensional example and this one-dimensional example, now I'm going to move to dimension 2. And I need some well, I don't need, but I leave you this this exercise, which which really tells me that when you see here, I take S1 cross S1, which is a topological space on its own, and we are very used to simply drawing this as a torus, and draw something like this. And when we do that, we are somehow using certain equivalence between this abstract space and certain drawing that takes place in R3, in three-dimensional Euclidean space. And so this exercise somehow asks you to show that this is actually valid, that what we do is indeed correct, where this picture is interpreted really as a surface of revolution of a circle. And then here you see it's the torus almost drawn. I didn't draw it completely because what I want to sketch more clearly is how the revolution functions. Right? So here you can see this is the circle that somehow one starts rotating around the z-axis. Yeah. Okay, and then here I give you a specific function, and I ask you to check that it is a closed embedding of this two-dimensional abstract manifold into this concrete closed submanifold, two-dimensional submanifold of R3. Okay, and then somehow with this in mind, I will just start drawing this as we usually do, as a surface of revolution. Now, having said that, I remember that what I was about to do was I was about to lift this one dimension up. Yeah. So from R and the circle, I moved to R2 and the torus, and I do it in the obvious way. Right? And this is a covering map, and you see, I'm identifying this with the corresponding surface of revolution. Somehow the pancakes stacked above V somehow schematically look as follows. So somehow you see the grid that you are seeing is really Z cross Z. So it's the points in R2, both whose coordinates are integers. Yeah, and of course each of the one not only has those, but one has the whole grid, and then inside one of them one takes this, right, and then somehow all the rest of the pancakes are just like all the possible translations of the original one by vectors in R2 with integer entries. And each of them in this picture is mapped homeomorphically onto this one that you are seeing here. A formal proof of that this is a covering map, I leave it to you as an exercise. Okay, and then the algebraic counterpart, which is when in R2 I just mod out the subgroup Z squared, and it's a covering map. And again, just as in the one-dimensional example, the two covering maps, somehow let's say the geometric one, or the one that arose from the exponential or from geometry or whatever, and the one that arises just algebraically, are essentially the same. So the two spaces are homeomorphic through a homeomorphism that allows me to think that this covering function is this one, but disguised. Okay, so we now have the one-dimensional example, a two-dimensional example, and then one can start thinking, okay, so whenever you have some topological group and then you take a quotient by some subgroup, you know, or well, here these are abelian, right? But let's say certain, if you take a group and then you mod out just you just consider the set of left cosets of some certain subgroup, then you are always going to have a covering map, right? From G to the from the projection from G to the set of left cosets. Okay, but that's not true, right? So that would be that one may be misled into thinking that that's the direction we are going to take, but it's not the case. And in this exercise, I ask you to give an explicit example of a topological group and a subgroup with the property that the projection is not a covering map. Of course, giving the set of left cosets the identification topology. And so the question is, okay, if it's not the case that these projections are always covering maps, what is it exactly that made our two examples covering maps? So what is the underlying property that makes them covering maps? And the answer is the following. The point is that they are not these are not only sets of left cosets. So they are not quotients given by modding out subgroups of a group, subgroups of groups. The point is that these ones are also orbit spaces, and it's easy to see that in these two examples. So Z acts on R. Z acts on R by means of the operation of R, right? Which is plus, which is translation. So Z acts on R by integral translations, and Z square acts in R2 again by the operation of R2, which is again plus. It's a sum of two vectors, sum of vectors, which is translation. So Z square acts on R2 by integral translations too. And if we think that way, so instead of regarding this and this as quotients of groups, and rather regarding them as orbit spaces, what we see is that what makes the projections covering maps is that the two actions, the actions by integral translations, they have this property that for each point on the space acted upon, so let's focus on this one. Let's focus on this one, on R2, act upon by z square by integral translations. It has the property that for each point in R2, there is an open neighborhood around it in R2 with the following property, that the elements of the group, which is z square, that don't move the neighborhood very far, that is, they don't move it very far, that is, that the intersection of the original one with the moved one is not empty, so it's not very far. So the only one that doesn't move that one very far is the identity. And every point has one such neighborhood. Right? So every point in R2 has a neighborhood with the property that every element of z square different from the identity moves the neighborhood sufficiently far away. That's somehow in the picture here, right? So if let's say I take my point y here, and then the neighborhood uy, so if that's the point y, the neighborhood uy would be this one, uy, and then you see every integral translation different from the from the identity function moves it sufficiently far away. That is, by sufficiently far away, I mean that the image doesn't intersect the original one at all, right? Or that the intersection is empty. And you see, it is this property, the one that allows to see that each of these is an open set homeomorphic to the original one. Since they are disjoint, their union is open, and so when they project each of them projects homeomorphically to this, which is open. Right? So this is the crucial property, that when considering this, actually these two as orbit spaces rather as quotients of groups, instead of as quotients of groups, the actions have this property, that every point has an open neighborhood with the property that every element different from the identity moves the neighborhood sufficiently far away. We say that the action is properly discontinuous in the strong sense. And so the terminology you are going to find in the books or on the internet is this properly discontinuous, and this in the strong sense. That's not standard terminology, but I like to use it, to contrast it with a weaker property that we are going to encounter later, and that we are forced to consider later on. And then the exercise, hand-in exercise, is to write a formal proof that these actions are properly discontinuous in the strong sense. So around each point, let's say of R2, you have to tell me concretely what neighborhood works. Okay, so that's that is this is what makes our maps covering maps. And now I want you to see the following. Let's move here to the picture we saw before. And now notice, I was talking about R2, but really it's also, I mean, it's also the complex plane. And if I think of this as the complex plane rather as like as if it were R2, notice that the integral translations are biholomorphisms of C, and this is obvious. So any translation is a biholomorphism of C. But so what does this mean? This means that you see, when I consider my open set in the torus evenly covered by the projection, so evenly covered by the projection, so that its pre-image under P is the disjoint union of all these open sets that I'm drawing, each of which is mapped homeomorphically onto my original V. You see, I can decide to use any of those open sets that I am drawing as a complex chart, as a chart for V. So I can use this one, or I can use this one, or I can use this one, etc. And then I have a bunch of possible charts, complex charts for V. And then to have a Riemann surface, what these charts must satisfy is that the transition functions should be holomorphic. But you see, a transition function, let's say from this one to this one, the transition function is precisely an integral translation, which is a biholomorphism of C. So starting with knowing now that this is a covering map, I have candidates for complex charts around any evenly covered V in the torus, and the fact that the original action was through biholomorphisms of C, so that set square acts through biholomorphisms of C. This implies that the transition functions are biholomorphisms, and then I can conclude that the torus has a Riemann surface structure. Well, a complex atlas, but it's obviously also a two-dimensional manifold, and with a countable topological basis. So it satisfies the definition of being a Riemann surface. And moreover, by construction, by how I'm defining the complex atlas for the torus, P is holomorphic as a function from C to the orbit space. So instead of writing Z square, I'm just going to write Z adjoin I, right? So the Gaussian integers. And this is what I'm stating here. So the torus admits Riemann surface structure with the property that the projection is holomorphic. Okay, so there are two things then that we are looking for. One is that our actions give rise to covering maps to the orbit space, and that can be achieved if one has a properly discontinuous action in the strong sense. And second, one would like that the action itself is given by holomorphism, so that the group that acts by holomorphisms on the given, well, in this case the complex plane, or on the given, let's say, open subset of the complex plane. And those are the properties that we are going to be looking for, because now what we have is, for instance, H, and let's say in the two models, U or D, each of which is an open connected set of C. And moreover, at least let's focus on the upper half plane. The orientation preserving Riemannian isometries, that is, the Mobius transformations that preserve U bijectively, they are by holomorphisms of U. So somehow we are all, this part 2 is kind of is covered, and then what we are going to be looking for is, we're going to be looking for subgroups of PSL2R whose action on U is properly discontinuous in the strong sense. That's what we're going to be looking for, and we're going to see that somehow in a way the theory is not perfect, and we are going to have to weaken this notion, and we are going to have to allow properly discontinuous actions that can, in the weak sense, and that is how we Fuchsian groups are going to arise.